Okay, so welcome back to SID2004 Bioorganic Chemistry Lecture 5. So today we're going to look at chemical synthesis of proteins and peptides. Okay, I'm going to go a bit fast because we have about 50 slides that I need to go through. So here we go. Okay, so this is just to show that we are here. Okay, and this one now is week 9. Okay, that one should be week 10, and then week 11, and then we're gonna stop here week 12. Okay, so I'm gonna try and cram all of these within 3 weeks. Okay, so last week we've looked at different type of protein structures. We've looked at primary structure, secondary, tertiary, and quaternary structure. We've looked at insulin as the case example that I keep on using for all these different structural levels. Okay, so what do we know so far? We know that protein is made out of multiple amino acid linked together via a covalent amide bond. Okay, valent amide. Okay, and we know that you can form an amide bond via a condensation reaction between a carboxyl group and an amino group. Okay, so it's simply um, it's simply just a nucleophilic attack at the delta plus carbonyl group, and you will have OH as the leaving group. Okay, so that's the basic principle. So we know that this reaction can work, but as always, it doesn't occur in nature very quick. Okay, so the reaction itself is not spontaneous. So you normally in lab you either need an acid or a base that act as a catalyst to get this reaction going. So you will see here how we can utilize that to produce peptides or proteins. Okay, so moving on, chemical synthesis of proteins and peptides. Again, even though the slides will be very long and I would say quite detailed, but this is an overview, and by no means will make you an expert, even if you kind of like repeatedly seeing this video again and again, right? Because the field of peptide synthesis and protein synthesis now becomes very broad, which I'm not gonna touch, because if I touch on that one, it becomes too broad, and we'll have, I don't know, probably 200 slides or so. All right. So when we think about conventional synthesis, where if you want to um, produce a molecule either by substitution reaction or elimination reaction, um, or by any chemicals or any chemistry that you're doing, especially if you looked at the first year chemistries that you did, where you did a qualitative analysis of elements, you prepare a Lezine test chemicals, you react it with some reagents. So basically what you're doing is you have a compound A, and then you mix it with compound B, you put it in a round bottom flask or conical flask or whatever, you stir it or you leave it at room temperature, and towards the end of the day you filter it, then you get your products, right? So that's the basic synthesis of for well, a conventional or a basic synthesis of anything in chemistry. So we will look at on how you actually do it for peptides, and then we will move on to a more modern synthesis. Okay, so imagine if you want to synthesize a dipeptide with a glycine and alanine. Okay, just these two. So what you will have is you will have A for glycine and B for alanine, and then, you know, as I've shown in previous slide, you just mix them, and in the presence of a catalyst, you will get an A and B, correct, right? So but in reality, what you can also get is not just A and B as what you expected. You can also get a B and A, right? You can also get B and B, and also you can get A and B, right? So you can have any of the mixtures, because towards the end of the day, if you look at your amino acid, all of them have two similar functional groups. So there's an amine and then a carboxyl. Okay, so as I was saying, so you can have multiple reaction, right? So you can have the carbonyl group from A reacting with the amine group from B. You can have the carbonyl from B reacting with amine from A. You can have carbonyl of one molecule of A reacting with an amine group of the same molecule of A. Because imagine again, um, in a reaction flask, you don't have only one molecule of A plus one molecule of B. You have 1 mole of A, for example, plus 1 mole of B. So you have millions and millions of molecules that can react and mix. And on top of that, if you only use A and B as it is, so the amino acid as it is without any protecting groups or without any modifications, what you can also get is a polymer, right? So you can have A reacting with A, reacting with another A, reacting with another A. You can get a polymeric chain of A, polymeric chain of B. You can get a co-polymerization of A and B, and so on and so forth. So it's uncontrolled. So to do conventional synthesis for peptide and proteins, you need to do a slight modification. Okay, and we will see it on the following slides. So again, it's problematic because you can have 4 products if you only have a few amino acids, and because the cycle can be repeated, you can get a polymeric reaction. Okay, so researchers a long time ago developed strategies where you can actually synthesize these molecules or peptides using conventional strategy, conventional approach. Okay, so mixing A and B, but then there are certain strategies included in it. Okay, so we look at the first strategy. So the first strategy is the introduction of protecting group, or if you see me abbreviate as just PG throughout this slide, then it means that it's a protecting group. Okay, so because you have two functional groups, an amine and a carboxyl, you can use two different protecting groups. So you can either protect the carbonyl, or you can either protect the amine, so that you can only have like one of reaction going. Okay, so as illustrated on the left hand side, so you can either protect the end like this. Okay, you can see it's rated in purple, and have the carboxylic functional groups free. Okay, and you can activate the carboxyl group, and then you can react it with another amino acid that is protected at the C terminal, at the carboxyl terminal. So if you do like this, you can only get one reaction going. Okay, so regardless of whether you have 1 mole or 100 moles of each molecule, you can only have one reaction going. So they can't be, it's impossible to get a polymerization. And of course, if this one is only an A and if this one is only an B, by doing this, you can only get one type of mixture. So now you don't have to worry about side reactions going, like B and A and A, and B and B, and so on and so forth. Okay. So, however, in terms of the strategy, there are a few things that you can actually do to kind of like very make it variable. Okay, so this is what I like to call as C to N, or N to C approach. Okay, What I mean by C to N is that you protect the N. Okay, for the first one you protect the N terminal, and then for this one you protect the C terminal, and then you react it together. Okay, so one will be the first molecule, molecule 1, and molecule 2, and the other way. And even though it's kind of like similar, so you protect the C, this one is protect the N. Even though it looks similar, but the sequence actually plays an importance, because imagine you need to grow your peptides, right? So you need to grow the peptide. You can either grow it like this, sorry, C terminal protected dipeptides, N terminal protected dipeptides. Right, so you can either grow it, so you can see the N terminal is always protected, and then you grow it that way, right? So this one is what I call as N to C. Okay, for the other round, you can protect the C, and then you grow it from the N terminal, C to N, meaning that C is one molecule and N is the other molecule. So you have kind of like a starting point there with a protected C, okay, protected C, and then you grow it and grow it and grow it, always from the N terminal of the original, right? So you add one peptide first, and once it's finished, you add another one, and then you add another one. Okay. In contrast, so this reaction, you protect the N, and then you grow it towards the C region. So the C terminal is always free. Okay, compared to this one, the N terminal is always free. So that's the difference between those two. Okay, so but the issue, so because you have two different options now, even though the first strategy you use protecting groups, and then hopefully you're hoping that protecting groups can actually help in synthesizing a purer peptides, but towards the end of the day, you have two different options that you can choose from to synthesize, to grow your peptide, and then only one of them are actually better than the other one, because the N to C approach, okay, actually can produce a lot of racemization from the carboxyl. I'm not going to touch about the mechanism on how you can actually produce racemization. You can look it up. It's very common. You just type in racemization of peptide C terminal, then you can see it very very easily. Okay, so the primary focus now is here. So the one in the middle. So where you actually grow the peptide um, at the N terminal always. Okay, so you grow it at the N terminal. We'll go through again in terms of the terminology as we go. Okay, so this slide is just as I mentioned. We have two functional groups, amine, which is a basic, and a carbonyl, which is acidic. Okay, so in this sense, to protect either or, so for a carbonyl carboxyl acid group, normally the approach is esterification, while for the amine group is acylation. We'll go and look at all of these reaction one by one. Okay, so the carboxyl acid group, esterification, amino acid react with alcohol in the presence of acidic catalyst, for example, hydrochloric acid gas. And under this acidic condition, the amino group protonates thus will not interfere with the esterification reaction. Okay, so when you have a chlorine, hydrochloric acid, which of course will form hydrogen and chloride ions. Okay, so it will protonate. Because hydrochloric acid is a very low pH, it will definitely protonate the primary amine. and while leaving the carboxylic acid functional group intact. So under this catalytic condition, the lone pair from the acid, the alcohol can react with the partial negative at the C of the carbonyl. Okay, so it's a basic simple esterification. I'm pretty sure you've learned about it in first year. So this reaction is under catalytic reaction, and you will form a C protected amino acid. Okay, so the benzyl ester can then be removed via hydrolysis with acid or base in aqueous solution to regenerate free amino acid if needed. So first off, you generate the C protected amino acid, you form a reaction, so you react it, and then you can remove this back to regenerate the free amino acid once it's already reacting with another amino acid. So okay, so esterification is used to protect COH, um, its removing its acidic characteristics. So you protect it, so you remove its acidic characteristics, thus preventing the carbonyl group from reacting in some undesirable manner, which can be anything. All right, so other common protecting groups of esters, for example, methanol, you can use ethanol, or you can use third butyl alcohol. Okay, so this is normally abbreviated as TBU, third butyl, TBOH for third butyl alcohol. Okay, and that one is ethanol and methanol. Okay, so these are some of the protecting group that you can use. Again, the different types of protecting group differs in terms of degree of protection that it can offer to the carboxylic acid group. Okay, remember electron donating, electron withdrawing, and so on and so forth. So those things that you've learned are actually applied here in terms of the degree of protection that it can offer. Okay, however, due to high probability of racemization from the C-terminal synthesis, this approach is hardly used nowadays. Okay, so the N to C approach is not feasible. Okay, so what I mean by N to C is that, say for example, you have a string of amino acid that you want to synthesize, and normally you write it as the N on the left and the C terminals on the right. What I mean by N to C is that the first amino acid starts at the N terminal. Okay, so you have your first amino acid, and you have your N with protecting group. Um, and so initially you have a free carboxyl, and then you want to add the second amino acid. Okay, so this is what I mean. So you grow the peptide from N to C. Okay, so this approach is not feasible again because of the free carboxylic acid. Not really, well, during the synthesis it's not really free, you actually protected it, but once you remove it and it becomes a free carboxylic acid, there are a lot of reaction that can occur. Okay, racemization is one of them. Other than that, in terms of heating, so what happens if you heat carboxylic acid? It forms a carbon dioxide, right? So there's a lot of reaction can occur if you were to synthesize using this approach. So it's not really feasible. So what you normally do is you synthesize a C to N. Okay, so protection can be carried out on the NH2 or COH group, and then or is actually you do it in both. So the first amino acid will always have um, C protected um, functional group. Okay, so the first amino acid is always like that with free N, and then the second amino acid will have a protected amino group with a free carboxylic acid. So you have the first one with a COH protected, and then it has a free amine, and then for your second amino acid you have a free carboxylic acid with amine protected functional groups. Okay, so this way you can have the reaction going. All right, so NH2 protecting groups via acylation. The most common strategy for protecting the amino group and reducing its nucleophilicity is to react the amino acid with carbonyl derivatives. For example, you can use benzoyl oxycarbonyl chloride or butyl dicarbonate. Okay, so an example is they call it as ZAC protecting group. So if you just Google ZAC protecting group, you can find this derivative or CBZ protecting group. So sometimes the abbreviation changes and there's a slight modification on the structure. On the other hand, you can also use bulk anhydride or um, butyl dicarbonate. Okay, so you can actually protect it as you will see on the next slide, or probably the other slide. Okay, so an acylation agent, for example bulk anhydride, converts the amino group to an amide, so you protect it via temporary amide. The reagent most commonly used for this purpose is butyl dicarbonate or bulk anhydride. An amino acid plus bulk anhydride will give you a protecting group which is known as butoxycarbonyl or simply called as bulk group. So in the next few slides or next slides until the end, you will see a lot of bulk written. So bulk is basically a protecting group on the N terminal. Okay, so how does the reaction occur? So of course, because you are aiming for a specific reaction going on with the amine group, you need to use a basic environment or basic catalytic environment. So that first off, you will deprotonate your carboxylic acid to become a carboxylic ion, which if you recall is non-reactive while leaving the amine group intact. Okay, so the lone pair of the amine will then react with the delta minus at the carbonyl functional groups. Electron will move, and then this bond will break, and the whole structure or part of the structure of the bulk anhydride will be as the leaving group. So towards the end of the day, what you will have is you will have a amino acid, okay, with an amide bond connected to a third butyl group. So this whole structure, okay, can be abbreviated as bulk. So you will see in some of the slides, I will draw it. This one should be a one single bond. Okay, this is one single bond. I will draw it as this. Okay, so these are the same. All right. So next, because bulk is an acid labile, so it's base resistance. So it can be removed using a very strong acid. For example, a trifluoroacetic acid. Okay, so trifluoroacetic acid, as you can see, the functional groups is an amide, okay. With a strong acid, you can break, of course you can break this bond, and also you can break this bond. And because this is an acid, so normally when you mix an acid with any compound, it produces a little bit of heat. So this heat promotes the formation of carbon dioxide. Okay, and towards the end you regenerate your amino acid. So if say you have one peptide over here, one amino acid, the first amino acid, then you have your second amino acid. Okay, now remember the carboxyl terminal is protected. Okay, and initially the N terminal is also protected using bulk, but with the treatment of TFA, you can actually cleave this bond, regenerate the primary amine, and you can add a third amino acid, thus growing the sequence. Okay, and remember this protecting group is um, acid labile, but you need to use a very strong acid to actually remove the first protecting group. Okay, as you will see, some example that we use is actually hydrogen fluoride to remove this protecting group. Okay, just moving on. All right, so strategies in peptide synthesis. We've looked at the first strategy um, in a liquid phase synthesis, or I like to call it conventional synthesis. Okay, so the conventional synthesis. So the first strategy is using a protecting group. So what is the second strategy? Let's go and have a look. So the second strategy is by actually using an activating agent, because as you remember, um, the carboxyl group and the amine group does not react readily. So you need to either have an acid or a base to actually catalyze the esterification and formation of an amide bond. But this reaction is actually very slow. Even with the presence of acid, it can be very slow. But then towards the end of the day, the complexity of the amino acid, because of the complexity of the amino acid, you want to avoid using an acidic or a basic environment during your synthesis. So normally you synthesize it in an organic solvent. So if you have these two functional groups in an organic solvent without the presence of acid or base, so the reaction it's not spontaneous at all. So therefore you need to use an activating agent. So in addition, in an aqueous sorry, in addition, in an organic mixture, in an organic environment, acid and base reaction occurs much faster than amide formation. So if you have a carboxylic acid with your first amino acid, for example, and you have an amino group um, from your second amino acid, what will happen is there will be an proton exchange, and you'll get a carboxylate ion and ammonium ion. Okay, so you instead have an acid and base reaction instead of an amide bond formation. Therefore, you need to use a specific reagent to actually activate this carboxyl group, so that instead of forming an acid-base reaction, it actually reacting the way that we wanted, which is a peptide bond formation. Okay, so there are many types of carboxyl activator, and we only discuss one type of it, which is carbodimide. Okay, example that will be used here is an N-dicyclohexyl carbodimide, or simply abbreviated as DCC. So DCC is one of the early generation of carboxyl activators in organic solvent. Okay, so other similar carbonamide reagents are such as DIC and EDCs. Nowadays, there's even third generation of carboxyl activators, which I'm not going to touch. Okay, so DCC activates the carboxyl group, by putting a good leaving group on the carbonyl carbon. So that's the structure of DCC, and that's the core of this first generation of carboxylic acid activators. So DIC has different years, I would say. Similarly, EDC has different groups altogether. So what happened here? So in the presence, when you mix an amino acid with a DCC or any carbonamide, what will happen is you form this intermediary activated species. So this species is very active, and as you can see, it no longer functions as the basic carboxylic acid. So in the presence of an amine group, it doesn't really form an acid and base reaction. So it forms an amide bond, as shown here. And then you have a urea base byproduct that you can simply remove by filtration. Okay, so although DCC lowers the energy for an amide bond to form, the reaction by no means free from other side reactions, as you can see on this section over here. Okay, so these are some of the side reaction that can occur um, when you activate an amino acid using DCC. For example, it can self-react with a free carboxyl group that does that have not been activated, forming an anhydride-like structure. And this anhydride-like structure can react with a free secondary amine, an amine group on the secondary amino acid, and forming um, something like this that blocks the synthesis altogether. Okay, so other co-activators or reagents are added to promote the formation of number 2 here. Okay, to minimize the formation of these unwanted reactions. For example, if you add a base, so once you add a base, the structure of this functional group is less reactive now. Okay, and if you put N-hydroxynilamide or NHS, as we call it, so you can also reduce the formation of these other byproducts, which we're not going to touch on the reactions and whatnot. Okay, so all in all, the summary of conventional synthesis. On the liquid phase synthesis, where you have N to C or C to N approaches, we have two strategies to actually promote an efficient synthesis. The first strategy is to use a protecting group, either on the N or the C terminal of the amino acid. And the second strategy is to use an activating agent to actually lowers the activation energy of your carboxylic acid functional groups. Okay, so since you can now synthesize peptides in a solution, okay, but there are also still drawbacks present. For example, when you have a mixture of a first amino acid, and a B, a second amino acid, including a base in the mixture, you have a reagent in the mixture, you actually have like so many multiple mixtures that might cause something that you don't know. Okay, so if this happens, the question is now, how do you separate them? How do you get only the dipeptide that you want so that you can proceed with the third amino acid coupling? Okay, so there's a lot of issues that you need to think about. So you can actually do that. Okay, you can simply do a lot of chromatography, right? So you can react with this the two first amino acids, and then you do chromatography. You get look at which fraction is actually pure. You take the pure fractions, and then you repeat the process and repeat the process and repeat the process. So you can actually synthesize peptides in a solution using the two strategies that we also mentioned. Okay, without the two strategies, it's almost impossible. But now using the two strategies, protecting group and activating agent, you can actually synthesize peptides and proteins. Probably not really proteins, more on peptides in a solution phase, but you need to do a lot of chromatography, which you will consume a lot of solvents and time. Okay, so therefore alternative mean is still necessary. So you still need to find an alternative mean where you can actually produce or synthesize peptide and proteins very easily. Alright guys, so I hope you enjoy the video or the lecture a little bit. I'm actually gonna cut this long lecture into two. So I'm gonna stop here at about 35 minutes, and the rest of it for another about 25 minutes I'm gonna put in for our Thursday lecture. And probably on top of that I will add in a little bit on the, admin degradation principles and lectures as well. Okay, all right, so have a good day, and see you guys around. Bye.